Hi guys, so I'm going to work through this SL test. So the first one says the most atoms of oxygen. Now remember, if it's O2 molecule of oxygen, each molecule has 2 atoms, or 2 times the amount of atoms. Okay, and how do we calculate the number of atoms? Well, it's going to be moles times by Avogadro's number, which is 6.02 times 10 to the 23. So the first one is going to be 64, so we're going to do 64 over 32, which is going to be 2 over 1, so it's going to be 2 moles, but there's 4 oxygens, so it's going to be 4 moles. Okay, if I look at C is the same mass, but it's O3, so that's definitely going to be smaller than that, so I'm actually going to ignore C. Okay, so the first one is going to be 4 times 6.02 times 10 to the 23, which is going to be 12 times 10 to the 23. Remember, we don't have a calculator for this. I mean, 1.2 times 10 to the 23. So they're not expecting you to work out exactly. Oh, excuse me, 24. So then B is going to be that number times 2. So that's actually going to be the same as A. And then if I look at D, it's going to be this number times 3, which is going to automatically make it bigger than either A or B. Okay, because obviously I do 3 times 1.2, and then it'd be times by 24, 10 to the 24. So it's going to be a bigger number. So the answer is D. Number 2, what volume of oxygen in decimeter cubed at standard temperature pressure is needed when 5 grams of butane undergoes complete combustion? So remember, we have calculators. They often do these types of questions where you're just putting the numbers into the formulae. So checking, do you know the formulae? 5.8 grams, so that's going to be mass over mole, so 5.8 divided by butane is C4, so 10, 48 plus 10, so 58. And they usually give you numbers like that, okay, so that you can work it out pretty easily without the need of something like a calculator. Okay. So I can do, so it's going to be 0.1. Oh, in fact, I don't even need to do that, do I? Looking at the calculations, I don't even need to work out the 58. So it's going to be mass over gram or mR, which is going to give you your moles. And then it's going to be moles times and then it's going to be moles times 22.7, excuse me. And then you need to do a molar ratio, so volume of oxygen. So it's going to be, at this stage, it's going to be a 2 to 13 ratio. Okay. So it's going to be your moles divided by 2. So it's going to be your mass over mR. Okay. And then you're basically going to divide that by 2, times that by 13, and then times that by 22, excuse me, 0.7. So straight away I can see D is wrong. So let's have a look at A. So 2 times is not, because that would be 2 over 1. I'm going to divide it by 2, so A is not correct. So B is going to be 5.8 divided by carbon times 4. Yeah. Hydrogen times 10. Yeah. Times 13 over 2, which is the same as doing that. And then times by 22.7. So it's going to be B. And A would be wrong is because we'd be, excuse me, dividing it by 13 and timesing it by 2. So we're going the wrong way with the molar ratio. So it's not C. Iron may be extracted from iron sulfate. It's ionically bonding. Describe the type of bonding in this solid. So we've got our positive and negative ions in like a lattice formation. So what's holding those together? What's an electrostatic attraction? So that's your first mark. Okay. And then you can say between oppositely charged ions. And extra second mark. Or you can be more specific and say between Fe2 plus and between Fe2 plus and S2 minus. Okay, so either of those things would have got you that second mark. So part 3b, outline in terms of electronic structure, why the ionic radius of the sulfide ion is greater than that of the oxide ion. Oops. So what is the sulfide ion going to be? So sulfur has 16 protons, which means it will have, under normal circumstances, 16 electrons. Okay, but if it's an ion, it's in group 16, so it's going to gain 2 electrons. So it's actually going to be, so sulfur, 2 minus, will be 16, that's just sulfur, protons, and 18 electrons. Okay, oxygen, under normal circumstances, will have 8 protons and 8 electrons, but the ion will have 8 protons and 10 electrons. Okay, so I'm comparing this to this. So this basically has the structure of neon, and this basically has the structure of argon. So we're effectively comparing neon and argon because they both got 2 extra protons, so that's not going to affect it. So why is sulfide ion greater than oxide ion? Well, because it has an extra shell, effectively, or extra energy level. So you could say the electrons are further from the nucleus. Excuse me. Or you could have, say, it's got an extra electron shell. Or you could say it's in the 3p rather than the 2p shell. You could give the electronic configuration, so you could say that S2 minus is 288 and O2 minus is 28. Electron shell energy level. So any of those would have got you the mark. So there's quite a few ways you could have worded that. Iron sulfide reacts with hydrochloric acid to form H2S. Draw the electronic structure of H2S. So if I wasn't sure, I'm going to draw my sulfur is in group 16, so it has 6 electrons. So 1, 2, 3, 4, 5, 6. It needs 2 electrons, and hydrogen can only share 1. So they're both non-metals. So it's going to be covalently bonded, so they're going to share electrons, plus they have to share for them to be able to make full outer shells. Okay, so that's what it's going to be. So we're going to have sulfur. We're going to have the 2 hydrogens coming off, and you can show this as dots or a line, however you want to, because it says the electron dot. This is the half Lewis structure. Okay, technically what I've drawn on the right is a dot and cross or full Lewis structure. Normally the full Lewis structure, you don't draw the circles, that's the only difference. Okay, but that's probably the easiest way of drawing it. If you didn't get the bond angle right, they actually allowed that as well, so if you happen to draw it like that, but you have to have your lone pairs paired up. Okay, you could have done it as lines as well, so we talked about how to work it out using lines previously, so you could have done that as well. Okay, and also straight with the 2 lines. Predict the shape. Well, it's got 4, so the geometry is going to be tetrahedral. Okay, we've got 2 lone pairs, so you can effectively see that the shape is like this, so it's going to be bent. Okay, tetrahedral never forms a linear molecule, so we know that the linear would not be correct. So you could say bent or V-shaped. Are they allowed angular as well? Okay, so any of those for the mark, and they didn't ask for the bond angle. Hydrogen peroxide can react with methane and oxygen to form methanol. This reaction can occur below 50 if a gold nanoparticle catalyst is used. So a 2-stage process. It doesn't matter, we don't know this reaction, we've never looked at it before, that's irrelevant. So we've got 8 grams of methane converted to methanol. So I'm interested in my 8 grams of methane. Let's give me that. And it tells me to use sections 2 and 6 of the data book. It tells me 3 significant figures, and I need the final volume of hydrogen. Okay, so first thing I can do is I can work out my moles of methanol. So I'm going to do my moles of CH4. Sorry, excuse me, methane, not methanol. So it's going to be 8 divided by, and remember we need it to 2 decimal places. You're using your data book. So 1605 is going to give me, and it says 3 significant figures. Mole should always be 3 significant figures. In my calculator, remember, I'm not rounding it, but I am there. So then I can work out my moles of hydrogen. Okay, so my methane to my hydrogen is a 1:3 ratio. So it's going to be 0.498 multiplied by 3. Okay. 0.498 by 3 gives me 1.494. So that's my moles of methane. And then to calculate my decimeter cube. Okay, and I almost missed that. Actually, we've got 2 moles here that are used up. So actually, out of those 3 moles of hydrogen, only 1 mole is left over at the end. So actually, my moles of hydrogen left is going to be 1 mole. So it's going to be the same as this, 0.498. Okay. And so then you're going to calculate your volume in decimeters cubed of a gas is going to be moles times 22.7 GCSE mode is going to be 0.498 times 22.7 is going to be 11.3 decimeters cubed. Okay, remember this is 3 significant figures, so you will get marked down if you haven't done that. Okay. Next one, what is the molar mass? So remember, molar mass is just mRam. What is the molar mass of a compound if 0.2 moles of the compound has 13.2 grams? Now, remembering you don't have a calculator again in these ones. So it's going to be mass over mole. Okay, so you're going to go, it's going to be 66. So that means these 2 are wrong. So it's going to be one of these 2. Well, you always write round to 1 or 2 decimal places. So it should be, should be A. Okay. Okay, question 7. Which of these molecular formulae are also empirical formulae? So remember, empirical formulae is your lowest whole number ratio. So can we reduce this whole number ratio? So 2 to 6 to 1. I can't reduce that ratio anymore. 2 to 4 to 2. I can reduce to 1 to 2 to 1. So that can't be empirical formula. And 5 to 12. I can't simplify anymore. So 1 and 3 could be empirical formula, but 2 can't because we can simplify that ratio. So we could have CH2O. What is the mechanism for the reaction between alkenes? So remember, alkenes are your double bond. And halogens, so that's your group 17 or group 7 from our GCSE. In the absence of light. So this means we don't have UV light to break that bond. Okay, so this is going to be an addition reaction. So group 17, remember, they usually exist as diatomic molecules, so Br2, Cl2, F2, etc. Okay, so it's going to be electrophilic addition. So because the alkene has a double bond, that means it's got lots of electrons, so it's really negative. So the thing that's going to be attracted to that is something that's electron attractive, okay, or electron loving. It's not going to be substitution because we're not swapping anything out, so we're not making any free radicals, so it's going to be addition, so we're adding that in. It's a bit like the bromine test for a double bond. Okay, so electrophilic addition, so it's going to be C. Number 9. Which volume of ethane gas, so there's your ethane, in centimetres cubed, so be careful on that one, will produce 40 centimetres cubed of carbon dioxide when mixed with 140, so we've got 40 centimetres cubed of this, and we've got 140 centimetres cubed of this. Now remember, the way we find out moles of gases is we're always timesing them by 22.7. So if we're timesing, the volume divided by, moles times 22.7. So we're always dividing it by the same thing. So actually our volumes will give us the exact ratio as well. So if we're sticking in centimetres cubed, so what volume do we need? So it's a 2 to 7 ratio. So if we've got 140 there, so that's like 14. So that's going to be 4. Okay, so it's going to be 40 centimetres cubed. So 2 to 4 ratio though. So we would need at least 20 centimetres cubed. To make 40 centimetres cubed. Okay, we can do this ratio, but it would make 80 centimetres cubed. Okay, because 40 times 2. Okay, so to react with all the oxygen, so the oxygen must be in excess, so we need 20 centimetres cubed of the ethane. Okay, bit of a tricky question there, that could have caught you out very easily. Number 10, which will react with the halogen by electrophilic substitution. Okay, so electrophilic, so it's got to have double bonds or something to attract with lots of electrons, so it's not going to be B or C. This is an alkene, remember. So they tend to do electrophilic addition, and benzene tends to do electrophilic substitution. Okay. So by that very nature, it'd be A, but also we've just answered a question previously on electrophilic addition of an alkene, with a halogen. Okay. An alkane with a halogen with UV light would be free radical substitution, but we don't have electrophilic substitution with it. Next one, chlorine undergoes many reactions. Mass spec is shown. So remembering, chlorine exists as Cl2. So these are going to be the atoms, and these are going to be the molecules of chlorine. Okay. So then it says outline the 2 peaks. So remember, Mz is mass over charge, and in mass spec the charge is usually +1. So anything over +1 is itself. So effectively Mz is around the MR, the mass. Okay. So why are there peaks at 37 and 35? And it's because there are the 2 isotopes of chlorine. Okay, and these 3 peaks at the end here would be from having like 35 and 37, or 37 and 37, etc. Okay. Number 11b, explain the presence and relative abundance of the peak at 74. Okay, so 74 is divided by 2 is going to be 37. So it's going to be 237 isotopes. So it's going to be a diatomic molecule, you could say Cl2, of 2 chlorine 37 isotopes. Remember, you can write chlorine 37 as in that way as well. Okay. And it says explain, so that's the presence, explain the relative abundance. Well, the one at 37 is really small. Okay, and it's because there's less of it. So the chlorine ratios 35 and 37 are usually a 3 to 1 ratio. Okay, and you can tell that from the RAM. So the RAM of chlorine is 35.5, so there must be more of that 35 isotope. So the chlorine 37 isotope is less abundant. Or you might say that's a lower probability of it. Okay, effectively meaning the same thing. So we've got a moles question here, so 2.67 grams. So that's already above it. Of magnesium oxide was added to 200 centimeters cubed. Now, whenever I see centimeters cubed in a question, unless it's asking me for the answers in centimeters cubed, I'm always going to go to decimeter cubed. So 1, 2, 3. So that's going to be, sorry, my pen keeps changing. 0.2 decimeters cubed. 1, 2, 3. Yep. So that's, we've got 0.2 decimeters cubed of our acid, and we have 2 moles per decimeter cubed. So remember, that can be also written as a capital M, means the same thing. So calculate the moles of magnesium oxide added. So this first bit, we just need that first bit of information. So it's going to be molar's mass over RAM, 2.67 or over molar RAM. And remembering, we're using the 2 decimal place numbers from your periodic table. So that's 86.94, which is going to, remember, moles and concentrations we always write as 3 significant figures. Okay. Next one, determine the limiting reactant. So it should be your MnO2 to HCl should be a 1:4 ratio, and we know that from our coefficients. So if I've got, so what I've got is 0.0307 of that, and my HCl is going to be 0.2 times 2. So it's going to be 0.4 mole, so 0.4. So you can see straight away that's times by, it's over 1/10 of it. So I can see straight away that I don't have enough of the MnO2, but what I could have done is times this number by 4, or divided that number by 4 to see if I had enough or not. So my MnO2 is limiting. And just doing the calculations like that will get you the mark, but you must state that it's limiting. So you actually got 1 mark for working out this, and 1 mark for doing the calculations and that it's limiting. And I would be tempted to do that times by 4. And it doesn't matter if you divide that by 4. Probably would be easier for me to divide that by 4. Let's just do it that way around, save me using my calculator. So if I divide that by 4, I get 0.1. So you can see I don't have enough of my manganese oxide, so that's why it's limiting. All right, and your calculations must show that. So you'll either divide that one by 4 or times that one by 4. Either would have got you the mark. Determine the excess amount in moles of the other reactant. So my HCl is in excess. So 0.0307. I'm going to need to use my calculator anyway. Times by 4 is going to be 0.123 moles. So that's how much would have reacted. That's how much HCl would have reacted. So how much have I got left over? Well, I started with 0.4. I used up 0.123. So I have left over 0.277 moles of HCl. Okay. Calculate the volume of chlorine produced the reaction is conducted at standard temperature pressure. So again, I'm always using that limiting. So my MnO2 to Cl2 is a 1:1. So it's going to be, 0.0307 moles of Cl2. How do I work out my moles? It tells you to use section 2. It's 22.7. So 0.0307 times 22.7 is going to give me 0.697. And remember, that's always in decimeters cubed. Okay, and it doesn't ask me. Just do it another way. Now, this one you can actually do by PV equals nRT. So if you've got it that way, you should still got roughly the same answer. And they will follow that through, but you would have to show you're working. Okay, It's a lot more complex method for that question. 11G, calculate percentage of mass of chlorine. So first I need to know what is the mass of the whole thing, and then what is the mass of the chlorine within that. Well, I have 2 atoms of chlorine. So 2 times 35.5. And then I'm going to divide that by, 4,5. And then I'm going to divide that by the MR of the whole thing. So if I work that out, that's going to be 120.91. So I'm doing the MR of the thing I want to know over the MR of the whole thing. A bit like if I got 10 out of 30 in a test, I do 10 divided by 30 times by 100 to make it into a percentage. It will give me 58.64%. And you would actually get a mark for calculating this RAM correctly, and a mark for this. So that's where your 2 marks come from. Number 12, what is the mechanism of the reaction between ethane? So we've got an alkene here. So remember, an alkane only reacts with free radicals because it's pretty unreactive, and it tells us it's sunlight, so we know there's UV light, and there's a halogen. So the only thing it can do is swap. So it's going to be a substitution. Okay, and chlorine with UV light produces a free radical rather than an electrophile. It's going to be free radical substitution. Okay. Number 13, 16 grams of bromine react with 5.2 grams of a metal. What is the relative atomic mass of the metal? So looking at the equation, it's going to be the metal plus bromine, because bromine always existed, Br2, making MBr2. So if we've got 5.2 grams of this, and we've got 16 grams of bromine, we're going to be making 21.2 grams of the Br2. So we can work out our moles of bromine. So it's going to be mass over RAM is going to be 16, because it tells us here, over 160, which is going to give us 0.1. It's going to be a 1-to-1 molar ratio, looking at that equation. So mass over mole will give me my RAM. So my 21.2 divided by 0.1, so I'm just moving my decimal place. So it's going to be 212 for my RAM, minus my 160. It's going to be 21 minus 16 is 5. So that's 52, so it's going to be C. Okay, so a lot of maths are actually for a multiple choice question where we don't have our calculators. So the next one, this is more the typical type of math question you get in the first one. So an antacid containing 0.5 grams of sodium hydrogen carbonate dissolved in water to give a volume of 250. What is the concentration in moles per decimeter cubed? Now it says of HCO3, okay, but it's going to be a 1, whatever moles I have for the whole thing, I have that many moles of the HCO3. So it's going to be 0.5 mass over RAM to give you my moles. Okay, and then concentration is moles over volume. But remember, I'd be dividing that by 1,000 or using 0.250. So it's going to be 0.5 over 84 divided by 0.250. Okay, so straight away I can rule out the ones with 250 in. And then 0.5 has to be over 84. And then, so if you've got 0.5 over 84, and then we've got 1 over 0.250 effectively. Okay. All right, so that's going to be B. So question 15, what is the molecular formula of a hydrocarbon containing 84% carbon with a molar mass of 142.3? So if it's got 84.6 grams of carbon, This is going to give me 100 minus 15.4 grams. So that's going to be divided by 1. That's going to be 15.4. Going to be divided by 12, which is around 7. Remember, we don't need to be too exact because we don't have our periodic tables or calculators on us. Oh, sorry, we do have a periodic tables, we don't have a calculator on us. So the mass of that would be 7 times 12. It's going to be about 84. I should have worked that out. Plus 15 is going to be around 99, say 100. So that means the MR is about 1.5 times that. So it's going to be like times 1.5-ish. And I can also look that my hydrogen should be double. So straight away I can cancel out B. And then double 1.5 is about 10. So it's going to be C. Okay. Number 16, the graph, shows the relationship between volume and pressure of a fixed mass of an ideal gas. So remember, as volume decreases, pressure would increase. Okay. So as volume increases, pressure would decrease. Okay. So if we look as volume increases in all of these, pressure would decrease. So I know that C and D are incorrect. Okay. And it wouldn't be a straight line, it would be directly proportional. So it's going to be A. 17, what's the number of atoms of oxygen in 2 moles of hydrated copper sulfate? Avogadro is constant. Okay. So the number of atoms of oxygen, in 2 moles is going to be 2 times however many atoms I've got in that whole molecule. So I have 3 in my sodium carbonate, and I have 10, so it's going to be times 13. Okay, so it's going to be 26 moles. And then to find the atoms, remember moles times Avogadro. So it's going to be 26 times 6. So it's going to be 160. It's not quite right, but about 160. So it's going to be 1.6 times 10 to the 25. If I move the decimal place, it's going to be D. All right, okay. 18. What is the volume in centimeters cubed of final solution if 100 centimeter cubed containing 1.42 sodium sulfate is diluted to a concentration of 0.02 moles? Okay, so we want to know how many moles are in our initial solution. And remember, we have calculated this, so it's going to be 1.42 over 142. So we're going to move the decimal place. 0.01. I don't know how to think about that. Moles. Okay, and that's in 100 centimeters cubed. So to find our initial concentration, it's going to be times mole divided by volume. Excuse me. My volume is 0.1 decimeters cubed. Okay, so we're moving our decimal place. So that'd be 0.1 moles per decimeter cubed. So that's our initial solution. We want to dilute it to 0.02. There's a couple of ways you can do this. I'm going to do C1V1 equals C2V2. So my initial concentration is 0.1. My initial volume was 0.1. My final concentration I want is 0.02, and my volume is what I don't know, so that's going to be divided by 0.02. So 0.1 times 0.1 is 0.01. So then if I do 0.01 over 0.02, that's 1 over 2. So that's 0.5. Okay, so 0.5 decimeter cubed, which should be 500 centimeter cubed. Long-winded question for a 1 marker. That's why you get 1.75 minutes a mark for this one. Which electron transition emits energy of the longest wavelength? So if it's emitting, then the energy is falling down. Okay, so I know B and C are incorrect. And then the longest wavelength is going to be low energy. So the shortest arrow has the lowest energy, so the answer is A. 3.26 grams of iron powder react with copper sulfate to determine the limiting reaction. So it should be a 1-to-1 ratio, so it should be not too bad to work out. So 3.26 over, and remember I'm using my 2 decimal place, 55.85 is going to be 0.0584 moles of Fe. Now I'm going to do concentration times the volume of this one, so this is going to be 0.2308 decimeters cubed. So 0.08 times by 0.2. So concentration times volume is going to give me my moles of my copper sulfate. So it's going to be 0.0160. Remember, I'm doing 3 significant figures. And that's my CuSO4. So it should be a 1-to-1 ratio. So which one do I have more of? I have more iron. So CuSO4 is the limiting. Okay, and you get a mark for working both the moles out, and a mark for saying that's limiting. Okay, but you can't get the mark for saying that CuSO4 is limiting without doing the calculations. All right, so just be careful of that. So going back here, we're using our limiting of copper sulfate. It's a 1-to-1 ratio, so we have 0.0, that's showing the calculations anyway. 20B, the mass of copper obtained was 8.72. Calculate the percentage yield. So we're going to do actual over theoretical. 160 moles of 0.0160 moles of Cu. So moles times RAM, 63.55, is going to give me my moles. So my mass, 1.0 grams. So that's how much our theoretical yield, that's the maximum we could have made. So 1.02 times 100 to get our percentage gives us 85.5%. Okay, there's a couple of ways you could have done it. They allowed 85 to 86%, but it had to be to 1 decimal place at least. Okay, so depending on how you did it. And for this method, you get 1 mark. Okay. There are many oxides of silver with the formula AgXOY. All of them decompose into the elements when heated strongly. After heating, there's my silver oxide. This much silver remains to determine the empirical formula. Okay, so we're heating it to decompose it into the elements. So AgXOY is becoming Ag and O2. So we have 3.760 grams, and we end up with 3.275 grams. So remember, the reactants must equal the mass of the products because atoms can't be created or destroyed. So that means for the mass of oxygen, it's going to be 3.760 minus 3.275 grams. It's going to be 0.4. 0.85 grams of oxygen. And then we're working out our ratio of Ag to O. So we're going to divide this by our MR of Ag, which is 107.87, which is going to give me 0.03036 moles. And then this is going to be divided by 16, because for the empirical form we're just using one atom, we're not using the O2. Is going to be 0.03031 moles. So it's close enough to be 1 to 1. Okay, so it's going to be AgO. Did not leave myself enough space for that. There's a couple of methods with most of these mathematical ones. Get a mark for working out the moles of each, and a mark for the excuse me, final answer. Okay, aspirin. So we've got 2.65 grams of our salicylic acid. And the MR is 138.13. We have 2.51 grams of the ethanoic anhydride. The MR is 102.10. Calculate the amount of moles of each reactant. So I'm just going to do mass over RAM. So we've got, excuse me, 0.0192 moles. Again, three significant figures. 0.0246 moles. And you actually have to do both of those for that one mark, but they basically give it to you anyway. Calculate the theoretical yield. So it should be a 1-to-1 molar ratio. So that means the salicylic acid is limiting. So we're going to use that. So it's going to be 0.0192 moles. Give us the MR of aspirin. Nope. Okay. So moles times by our RAM. There's a couple of ways you could do the RAM quickly. You can either add up each atom, or you can say, well, it's this whole molecule added to an H2, added to COCH2, because that's what we've added. So you can do the MR that way. I think that's the quickest way. So 180.17 is what you should got for the MR, and that gives you 3.46 grams. Okay, so I'm doing my maths to 2 decimal places. If you worked out the first one wrongly, you are allowed error carried forward marks, so long as you use the limiting reactant. So 23, in which mixture is NaOH the limiting reactant? So NaOH and H2SO4. So I can either do the whole ratio, or I can work out that I need 2 of those for 2 of those. So it should be 2 to 1, whereas the HNO3, these are going to be 1 to 1. Okay, but I could have written out my whole equation if I wanted to. So 0.2, so they're the same. So it's not going to be that one. So that's only half what it needs to be, so that it's limiting in that one. Just double check the others. It's 1 to 1, so it's too much in that one and the same in that one. So it's definitely B. Last page, number 24, the complete combustion of 15 grams of hydrocarbon produces 60 grams of carbon dioxide. What is the molecular formula of X? So this is a particularly challenging one to have, especially for a multiple choice. So you've got hydrocarbon, I'll just call it HC, plus O2 makes CO2 and H2O. So we've got 60 centimetres cubed of this, 75 centimetres cubed of this. All volumes are measured at the same temperature and pressure. And we have 15 centimetres cubed of this. So we're looking at our molar ratios. This is 1 carbon and this is 2 hydrogen. So because this is our molar ratio, we're saying how many times does 15 fit into 60? So 60 divided by 15 is 4, so it's going to be C4. And then 75 into 15 is 5. But remember, each one has H2, so it's going to be times by 2, so it's going to be 10. We C4H10, so it's going to be C. Which propagation step in the free radical mechanism of ethane with chlorine? So propagation step, so the initiation step is going to be making the free radicals. So the propagation step is either going to be, where are we? Ethane, so C2H6 plus a chlorine free radical, making HCl and our C2H5 free radical. Or it's going to be our C2H5 free radical reacting with chlorine to make C2H5Cl and a chlorine free radical. So this would be our initiation, and this is our first propagation, our second. It doesn't ask for first or second. So that's initiation. 2 free radicals going to 1 for C is termination. So B and D are both reacting with a free radical. So B could be correct. And C, we don't get hydrogen free radicals, so it has to be B. So I didn't even need to work that much out. Why do gases deviate from the ideal gas law at high pressures? So the molecules have a finite volume. That's true. Cohesive forces increase the volume from the ideal. That's not true. Increasing the pressure increases the temperature. That's not true at high pressures. Okay, so it's definitely A. 27. Which mechanism does benzene undergo? So benzene's got double bonds, so it's going to be electrophilic. And it can't undergo addition because of the negative inductive effect. It pulls the electrons back in. So it's electrophilic substitution because benzene's too stable to lose those electrons. Okay, I hope that helped.